Bismillah, Alhamdulillah, Assalatu wassalamu ala Rasulillah, Sallallahu Alaihi Wasallam, wa ala alihi wa ashabihi ajmain. Allahumma salli wa sallim wa barik ala nabiyyana Muhammad, Sallallahu Alaihi Wasallam. Assalamu alaikum. I would like to welcome all of you in this session where we'll be talking about informed design process to address CEP and CEA. CEP and CEA. CEP is basically complex engineering problem solving, and CEA is complex engineering activities. So inshallah, we'll try to discuss these two important things related to engineering education, inshallah. So first of all, learning outcomes. We'll talk about learning outcomes. After that, we'll try to discuss about the informed design process. And I want to highlight one important phenomenon which is happening in engineering education, which is Washington Accord, an international accord. I'll try to highlight that. Then few comments about outcome-based education, or OBE. Then already you know that we are implementing outcome-based education in our ME program. In this ME program, we are already accredited by BAETE, BAET, or some people say BAET. We are already accredited by them, and our system is basically, what we are required to do is there is a kind of code 12875. So 12875, in this engineering program, our graduates, they must attain 12 graduate attributes, these 12 graduate attributes, 8 knowledge profiles, 7 ranges of complex engineering problem solving, and 5 ranges of complex engineering activities. So this is the engineering education, curricula prescribed by Washington Accord, which we'll discuss after some time. And today, my main focus will be to highlight this and these things, inshallah. Also, I'll talk about CEP and CEA reporting, which all the projects must do. And finally, I want to show you how different stages of informed design process, different processes are addressing different CEP and CE ranges. That will be the last thing we want to discuss today, inshallah. Okay. Now, first of all, regarding the learning outcomes. So hopefully after today's session, you will be able to explain the 8 stages of informed design process. Also explain outcome-based education, explain the 12 graduate attributes, 8 knowledge profiles, 7 ranges of complex engineering problem solving, CEP, and explain the 5 ranges of complex engineering activities, and finally relate informed design process with different ranges of CEP and CEA. These are the learning outcomes for today's presentation session. Now, let us once again revisit informed design process. I'm using the acronym IDP. What is this thing? How many ranges are there in the informed design process? I want to hear from our participants. Who can tell me how many ranges are there? In the very first class session of machine design sessional, we discussed that. Who can tell me how many ranges are there? You can raise your hand, virtual hands. So how many ranges are there in IDP?
Sir, 8 stages.
There are 8 stages. Yes, there are 8
8
stages.
stages.
Yeah, correct. There are 8 stages. Now let us explore these 8 stages one by one. The first stage is clarify problem specifications and constraints. That's the first thing. Followed by research and investigate. Then generate alternative designs. That's the third step, where you have multiple solutions. Then you choose and justify the optimal solution, followed by develop a prototype. Then you need to test and evaluate this prototype. Then if needed, and usually that's the case, usually you redesign the solution. And you know, design process is iterative. So you might come up with a very good design after several iterations, several loops. And finally, you communicate your achievements. So these are the 8 steps in informed design process. Okay. Now, let us talk about Washington Accord. This is an international accord, yeah, an international agreement between bodies responsible for accrediting engineering degree programs. For example, in Bangladesh, this, as I mentioned earlier, BIET is the accreditation agency in Bangladesh. In the US, you already saw the definition. In the US, it's ABET. And ABET is accrediting MIT, Stanford, and those renowned universities, their programs. So this is an international accord. And there are many signatories. These are the permanent signatories. Right now, there are already 23 signatories. And you can see some of the neighboring countries are already there. India, even Indonesia, Pakistan, Sri Lanka, those countries, neighboring countries are already there. Malaysia is there already. Yeah, Malaysia is already there since the year 2009. Bangladesh is yet to get the permanent or full signatory status. So right now, there are these 7 countries who are waiting. They're in the process of becoming permanent member. Yeah, Bangladesh is in process. Hopefully, I'm hoping by the middle of next year, inshallah, Bangladesh will become a permanent signatory as well. The benefit, I mean, what will be the benefit? The benefit of this this accord is that these signatory countries, they recognize each other's degree. So suppose a degree program in India, suppose a program is accredited in India, that will be recognized by Indonesia or United States, UK, South Africa, Australia, Canada, all those countries. Yeah, that's the beauty of this accord. So I'm hoping, inshallah, Bangladesh will enter into this Washington Accord as a full signatory. Then, I mean, the programs accredited by it will be recognized by all those countries. So that's the beauty of this Washington Accord. So I'm hoping and praying that Bangladesh will get the full signatory status by the middle of next year, inshallah. You should pray as well. Now, Washington Accord, as I was telling earlier, Washington Accord demands that the accreditation agency should accredit, they will give accreditation to engineering programs where they have this, as I mentioned earlier, 12, 8, 7, 5 thing. That means in those programs, they should have 12 graduate attributes, 8 knowledge profiles, 7 ranges of CEP, and 5 ranges of CEA. So that's the requirement from the Washington Accord. So Washington Accord also wants that OBE, is implemented. I mean, outcome-based education. So these are the things we are addressing, yeah, here at OST.
Sir, what is mean by CP CEA?
CEP is complex engineering problem. CEP is complex engineering problem. We'll talk about it later. Yeah, we'll talk about all these 7 ranges later on, inshallah. The complex engineering problem solving ranges. And also we'll be discussing the 5 ranges of complex engineering activities later on, inshallah. I hope you'll understand them, inshallah. Now, let's move to OBE, outcome-based education. Outcome-based education. Any idea about OBE? What does it mean? Outcome-based education. Already we have 48 participants. What is meant by OBE, outcome-based education?
Sir, so it is outcome-based education. After learning this course, after finishing this course, what we will learning?
Yeah, in terms of outcomes. Yeah, thank you.
Is
So it's basically OBE is an education theory that bases each part of an educational system on goals. Goals or outcomes. Goals or outcomes. When we say goals, these are basically broader terms, but outcomes are more specific. More specific. Usually they are expressed with action verbs. Action verbs. Now, according to another source, outcome-based education means clearly focusing and organizing everything in an educational system around what is essential for all the students to be able to do successfully at the end of their learning experiences. Okay. So this is critical thing, that essential for all the students to be able to do successfully at the end of their learning experience. For example, you will see after some time that one of the graduate attributes which you should have is communication. So communication skill is extremely critical, extremely critical, and we are trying to address that in many courses. Several courses are addressing communication skill. For any program, you had a communication seminar, right? Communication seminar. So that is related to that graduate attribute directly. So that's OBE, and in OBE, the faculty of a program reaches consensus on a set of program learning outcomes, knowledge, skills, and attitudes. In OBE, you'll see this thing, KSA. KSA means knowledge, skills, and attitudes. So it is expected when the students are graduating, they are graduating with certain knowledge, certain skills, and certain attitudes. For example, a while ago, I discussed about communication skills. That is one of the critical skills which you should have when you are graduating. Of course, you should have some nice attitudes, so ethical values. You should have some basic knowledge about the main mechanical engineering related disciplines. So all these things are there in OBE. Now let us discuss about the 12 graduate attributes, and these are coming from where? Yes, of course, that's our accreditation agency, BIET, but BIET is getting it from WA. What is WA? What do you think? What is WA?
Washington Accord.
Yes, Washington Accord. Washington Accord. Washington Accord is giving, directing, BIET to adopt these 12 graduate attributes prescribed by them. These are all prescribed by them, the Washington Accord. Now, there are 12 graduate attributes prescribed by Washington Accord. And the first 5 of them, and we denote them with POs, yeah, PO1, PO2, PO3, PO4, PO5. These we denote them with POs. So the PO1 is related to engineering knowledge, PO2 problem analysis, PO3 design and development of solutions. Now this is machine design course, yeah, the sessional of this. This is directly related to this PO3. PO3. Also investigation, research and investigation. Also you should have, you should have the knowledge of different modern tools. So these are 5 POs which are related to core engineering science. Core engineering science. Also, you have 3 POs related to professional responsibilities, like PO6, 7, and 8. Yeah, these are related to these responsibilities. PO6 is related to engineer and society. PO7 is related to environment and sustainability. PO8 is related to ethics, which is very important. One of the most important graduate attributes is ethics, which we denote ethics with PO8. These are all related to responsibilities or professional due diligence. And finally, we have 4 other graduate attributes which are required in workplaces. And they are basically professional engineering practices. They are related to that. Like PO9 is related to individual work and teamwork. In this course, you have groups. You'll be working in groups. So that will be addressing the teamwork skill. Also, you'll have to work individually as well as a part of a team member. So that's related to PO9. As I mentioned earlier, PO10, which is communication. This communication skill is extremely important. This is basically related to these complex engineering activities, CEA. You will see that later on. So PO10, communication, is directly related to complex engineering activities. Then PO11 is related to project management and finance. And finally, PO12, that's the 12th graduate attribute, which is related to lifelong learning. So your learning should not stop when you graduate from this program. You can say that's just the beginning. You should continue. You should continue. That is a skill. And some students, I hope all of you will achieve that. When you are working in the industry, you know how to get information, how to solve a problem, how to learn new things. You will not be static with things you learn in your bunch of courses here at OST. So lifelong learning is a very, very important skill, by the way. So these are the 12 graduate attributes our students should have as per Washington Accord. Also, Washington Accord is demanding the engineering graduates should have 8 knowledge profiles. 8 knowledge profiles. Those are related to natural sciences, mathematics, engineering fundamentals, specialist knowledge, engineering design, and again, machine design sessional. You can see is directly related to this K5 or engineering design. Then also engineering practice, comprehension, research literature. In this IDP, informed design process, the second step or phase, whatever you call it, that is directly related to this research literature, directly related to that. Okay. So it is already embedded in your curriculum. All these 8 knowledge profiles, they are embedded in the curriculum, mechanical engineering curriculum. So we are addressing at different levels, yeah, in different courses. Now we come to CEP, complex engineering problem solving. Let us go through different stages. So before we move to complex engineering problem, you should know the problems can be of different types. There are some problems which are well-defined engineering problems. In fact, most of the time, I mean, so far, this is what you have been doing. A well-defined problem. There will be a single, most of the time, single answer. Yeah, you are familiar with that. You have done those kind of problems in your thermodynamics, in solid mechanics, and other courses. You have seen that. Also, there are some problems which are not exactly well defined. They are broadly defined. Broadly defined. So there can be multiple answers. And the highest thing or highest level is complex engineering problems, which are basically faced by the engineers in workplaces. When you go to your workplaces, frequently you will be encountering problems which are not well defined or broadly defined. Not at all, I mean, loosely defined rather. Loosely defined. So you will be struggling as a professional engineer, how to define this problem. What is this problem? How to solve this problem? This is quite frequently you will be having in real field, in real life. So the people of Washington Accord, they were trying to define complex engineering problems with the help of 7 stages, which we'll discuss later on. Yeah. So this in international agreement, IEA, they have these 3 different accords. This Washington Accord. This Washington Accord is focusing on complex engineering activities or projects which require in-depth knowledge, excuse me, that allows a fundamental based first principles analytical approach. You know, this they have, IEA has other accords as well, Sydney Accord, Dublin Accord, but those are for technicians or technologies. But for professional engineering graduates, they should have these complex engineering activities or projects, which we're trying to do in this course. Now, as per Washington Accord, there are 7 ranges of CEP. Like P1, related to depth of knowledge required. P2, range of conflicting requirements. P3, depth of analysis required. P4, familiarity of issues. P5, extent of applicable codes. P6, extent of stakeholder involvement and conflicting requirements. And P7, interdependence. So these are the 7 ranges. So here, as per Washington Accord, they are saying complex engineering problems have characteristic of P1 and some or all of P2 to P7. So in order for a problem to become, I mean, if you want to have a complex engineering problem, P1 is a must. This is a must. P1 should be there. Must. P1 is must. And then from P2 to P7, you can have some or all of them. So I would say at least 2 to 3, at least 2 to 3, at least. Now you might be wondering, what's the big deal? Yeah, it's a big deal because now you'll be selecting your projects. When you select your projects, it should be complex. It should have CEP and CEA. So in the problem the title which you'll be proposing, it should have a complex engineering problem where you have, of course, P1. So there should be some depth of knowledge which will be required. And also they should have some of these 2 to 3. I would say at least 2 from P2 to P7, at least 2 or 3. It will be nice if you have all of them, all 6, then that will be super complex, but that's not required. I mean, you don't have to have all of them. Frankly speaking, when we in most of the projects, if it is a serious project, this P1 will be theirs, it will be satisfied. And usually you will see most of the time they will have some conflicting requirements. It's quite typical. Conflicting requirements are quite typical. And usually we give you projects where these are not familiar, little bit unfamiliar. And we give you projects where usually they are not defined by established codes. So don't get frightened. You will see later on, some of these, at least these three, will be fulfilled by most of the projects. Even this interdependence, most of the time when you have projects, you have different subcomponents. Usually they depend on each other. That is interdependence. So even interdependence is most of the time, I would say, this is there available. Now these terminologies are new to you, I think. Yeah, these are new, but they are not uncommon. They're quite common in different projects, as you will see later on. I will show you an exemplar later on, inshallah. Now, let's say a little bit about P1. P1 means depth of knowledge required. So it cannot be solved without in-depth engineering knowledge at the level of one or more there are different case knowledge profiles. From where you're getting this? Yeah, you're getting this from here. Remember earlier I told you there are 8 knowledge profiles. It's coming from there. There are 8 knowledge profiles. So in P1, you should have one or more from K3, K4, K5, K6, or K8, which allows a fundamental based first principle analytical approach. Okay. So you will see later on, usually it's there. Yeah. When you say K3 knowledge, it means some of the first courses you took in your engineering program, like thermodynamics, for example, heat transfer, for example. Yeah. This machine design course, what you have, it will fall under K4, basically. So in your complex engineering projects, you should have at least, usually you will see, you will have K3 and K4. These are, most of the time, they are available already. Also, P2, range of conflicting requirements. So it means involving wide-ranging or conflicting technical, engineering, or other issues. Like you might ask the question, what constraints are placed to resolve the problem? Constraints. In all the design problems, usually you'll have constraints. Can you give some examples of constraints? Who can give me some examples of constraints in different design problems?
So high material cost.
Okay, material cost. So cost constraint. Okay, good. What else?
Time constraint.
Time constraint. Exactly, time constraint. So the product, maybe you'll have to fabricate within certain time. So time constraint is, yeah, can be there. Sometimes you don't have enough time to develop a product. Yeah, so you'll have to move in a fast track. Yes. What else? Any other?
The manufacturing constraints.
Yeah, manufacturing. Maybe it's a very nice concept, but you don't have the required manufacturing facility. You'll face that in your projects. You will see sometimes you will be constrained by manufacturing facilities, and also sometimes you'll have conflicting demands. You want to develop a very energy efficient product, but if in order to make it energy efficient, the product will become very expensive, which nobody will buy. So these are conflicting demands. Yeah, so you might have a very nice product, but aesthetically it's not pleasing. It doesn't look good. Yeah, you might have that kind of issue. So these are typical in projects. Now, P3, CEP has, as you know, 7 ranges. This is the 3rd range. P3, depth of analysis required. What does it mean? Have no obvious solution. It's not well-defined problem. You have a single answer or single approach. So no obvious solution, and require abstract thinking or originality in analysis to formulate subtle models. Yeah. So basically what it means, you can see it clearly here, multiple solutions, not a single solution. You can multiple solutions. I think in most of the project, usually P3 is there, usually. It's quite typical. P4, the 4th range, is familiarity of issues. So involve infrequently encountered issues. Yeah, so it's a new problem. Yeah, new problem, not previously or only rarely encountered. So you might have some products which are a little bit novel, or the approach is novel. So that will be related to P4. P5, it's straight cut, extent of applicable code. So basically, as your project should not be like, I mean, it should not be already available in one of the codes. You know, there are different agencies, they're establishing or they're publishing codes. Can you give me some professional bodies who are publishing or setting codes? Who can tell me some professional organizations, name of professional organizations?
Sir, ISO.
ISO, correct. ISO. What else?
PSTI probably. I'm not sure about it.
Yeah, BSTI. Okay. What else? What about for mechanical engineers? There are some dedicated professional societies. What are those societies? And we have student chapters of those societies.
ASHRAE.
IMECI and also
ASHRAE.
ASME. Then ASHRAE. ASHRAE, you know, for HVAC, their codes are
Refrigeration and air conditioning.
Yeah. So ASHRAE is really giving all the codes in HVAC, heating, ventilation, and air conditioning. ASME has codes for different things for pressure vessel design and so many other things. So your project should not be there in one of the codes already. I mean, it should not, then there is no point of, I mean, then there is no complexity. And frankly speaking, most of the time, in many cases, you don't have clear, I mean, the codes or standards are not there. Yeah, it's you need to develop some sort of standards. So in order to fulfill this P5, your project should not be readily existing in standards or codes. Now the 6th range, 6th CEP range, is related to extent of stakeholder involvement and conflicting requirements. Yeah, you know, as I said earlier, that you might have different stakeholders. Can you give me, when we say what are, I mean, stakeholders? Suppose you are you have designed a ceiling fan. Who are the stakeholders? You suppose you are working in one of the industries which is designing and fabricating and selling ceiling fans. Who are the stakeholders?
Sir, the board of directors.
Okay, board of directors, correct. Who else? What about consumers? They are not stakeholders?
Yes, sir.
Of course, your manufacturing, you have technicians in the manufacturing facilities. They are not stakeholders? Yes, they are stakeholders. Yeah, so there are many stakeholders, and they have different
shareholders.
Exactly. Shareholders are also stakeholders. So their requirements might be conflicting. I mean, conflicting with each other. This P6 is related to that. P6 is related to that. Finally, the seventh range is called interdependence. So there are high level problems including many component parts or sub problems. So basically the problem is able to be broken down into smaller components or sub problems, not physically but mathematically. It can be mathematically as well. Yeah. So these are the 7 ranges of CEP. Any question or comment about this CEP? Any question or comment? Do you need any clarification for these 7 CEPs? 7 ranges rather. So in your project, you should have, I'm repeating that one more time, you must have P1 and you should have 2 to 3 from the rest. And most of the time you will see you can fulfill that. It's not a big deal. Inshallah. Okay, any question or comment? If not, then we can move to the next thing, which is CEA, complex engineering activities. Complex engineering activities. I told you earlier, this CEA is related to one graduate attribute, one important graduate attribute. Who can tell me what is that? It's related to one of the 12 graduate attributes. You know, there are 12 graduate attributes. This CEA is related to one of them directly.
Sir, research literature.
No. PO10. What is PO10? Communication. Communication. CEA is related to communication. This here you can see, this is one illustration where this WA means Washington Accord 10, which is, we call it PO10. So this CEA is related to this communication skill. Communicate effectively on complex engineering activities with the engineering community and with society, able to comprehend, write, present, give, and receive instructions. So this CEA is related to written, verbal, and other form of communications. So you will be preparing reports, prototype drawings, you'll be delivering verbal presentations, viva, etc. So these engineering activities, should be complex. And now, just like CEPs, there are ranges in CEA. There are 5 ranges which were prescribed by Washington Accord. 5 ranges. So according to them, complex activities means engineering activities or projects that have some or all of the following characteristics. And they have given these 5 ranges related to range of resources, level of interaction, innovation, consequences for society and environment, and familiarity. We very quickly go through them. So the first one, A1, we define it with different A's. A1, range of resources. So involve the use of diverse resources. Diverse resources, as for the purpose resources include people, money, equipment, materials, information, technologies, etc. So you're dealing with different types of resources as engineer. In the field, engineers, they deal with different things. There are public functions. They handle financial matters. They handle different types of equipment, materials. They gather different information, disseminate different information. They deal with different type of technologies. So there should be different range of resources, not single thing. Usually you have multiple resources. So this range is related to different range of resources. Next level is range is related to level of interaction. So this one require resolution of significant problems arising from interactions between wide range or conflicting technical, engineering, or other issues. Yeah. And the third one is related to innovation. Fourth one is related to consequences for society and environment. And the fifth one is related to familiarity. So related to new experience. So these are, I wanted to have a very brief presentation. So that's why I'm not going into details, further details, which you can explain you during the weekly meetings. Your project advisors can clarify this later on, inshallah, if you need more clarifications. Now, we need to do the CEP and CE reporting, and we have developed a template, which I'll show you later on. Yeah, we have developed a template, and which you should be using for each project. This template should be used, and it should be filled out. I will show you one example today, inshallah. Okay, and it will be shared with you, inshallah. Now, the last topic, you already saw these 7 ranges of CEP and 5 ranges of CEA. Our IDP, how it's addressing them, this is what I'll try to discuss now. Yeah, IDP is, as I said, there are 8 stages. As you will see, each one of them, they are related to certain ranges of CEP or CEA. For example, the first thing, which is clarify problem specifications and constraints. So you need to describe the problem clearly and fully, noting constraint and specifications is directly related to at least P2 or P6. Yeah, P2 or P6. Also, you talk about constraints. When you say constraints, what does it mean? Limits imposed upon the solution. Limits imposed upon the solution. Earlier you mentioned time constraints, yeah, materials constraint, manufacturing facilities constraint. So many constraints can be there. So also specifications. Specifications means the performance requirements the solution must meet. The performance requirements the solution must meet. This is the specifications. So suppose in the case of ceiling fan, what might be the specifications from your employer? What do you think? What might be the specifications? So you are working as an engineer in one factory. They are fabricating ceiling fan. What might be the specifications?
So how many blades will be there?
Okay. Thank you. What else? What about the speed? Speed
Sir,
of the fan.
Speed of the, yes sir, speed of the fan.
Yeah. What about the aesthetics?
Price.
Price is very important. Exactly.
Price.
Yeah. The price should not be more than, let's say, 5,000 taka. Yeah, it's very important. I mean, specifications. Yeah, they might tell you, oh, I mean, noise. It should not make noise, and things like that. It will be specified. So in your projects, in the first step, this is what you'll be defining. You'll be defining, and you'll be specifying different things. Also, you'll impose the constraints. Okay, now the second step or stage in your IDP is research and investigate. So you'll have to gather information related to P2 to P7. You will see that you will have to gather information as much as possible. So you search for and discuss solutions that presently exist to solve this or similar problem. So usually you don't start from scratch. usually you don't start from scratch. Usually you see some of the best practices. So in the case of ceiling fan, you will see what are some nice models available in the market, why people like it, what are the distinguishing features they have, the successful fan models. Don't you think you should explore those things? Yeah, agreed that you'll have to basically
Yes.
research and investigate. You see what are the available things there. You might explore the new materials which are available in the market. So this research and investigate is very important related to these ranges from P2 to P7. Then generate alternative design. That's the third stage in your IDP, and you'll have to brainstorm and try to find out multiple solutions. Multiple solutions is related to P3. Remember, it's directly related to P3. And you don't stop when you have one solution that might work. You need more solutions. You continue. Actually, what we'll ask you in your project work, we want you to develop at least 3 solutions, preliminary solutions, 3 alternative designs, from which you will select the best one. So you continue by approaching the challenges in new ways, which are related to P4 and A5. You describe the alternative solutions you develop related to P1 and all the ranges of complex engineering activities. Then you choose, and you suppose you have 3 alternative design, you select the best one. You select the best one and you optimize it. As I said earlier in one of the class sessions, that design and optimizations, they go hand in hand. They go hand in hand. Always you'll have to optimize. So in the previous step, yeah, you have your multiple solutions, at least 3. You select the best one and then you optimize. You use engineering, mathematical, and scientific data and employ analysis techniques to justify why the proposed solution is the best one for addressing the design specifications. And these are related to P1, P3, P5, this CEP, these CEPs, and also A1, A3, and A5, these CEAs. Yeah, I hope you are understanding what are meant by this. These are color coded. The blue colored ones, these are related to CEP, and these green ones are related to CEA. And this chosen alternative will guide you preliminary design. So you should have conflicting requirements, should be an innovative design. Yeah, the optimal solution, what you are developing, it should, have, these are already, it should be there. Yeah. Then you develop a prototype, you make a model of the solution related to P1 and P5 and things like that. And when you develop a prototype, you can use CNC machining or additive manufacturing. When you say additive manufacturing, you have 3D printing. And already you know that we have the CIM lab where you can do 3D printing free of cost. Also, sheet metal working is there, metal casting, and more. There are different manufacturing techniques for developing your prototype. Once you develop the prototype, you go for production or manufacturing and things like that. Then the next step in your IDP is test and evaluate the prototype. So you develop a test to assess the performance of the design solution. And these are related to these 3 ranges of CEP, P1, P3, and P5. You collect performance data related to A1, the first range of CEA. Yeah. So, you can explore. These slides will be shared with you. You can see that, that's the beauty of IDP. If you do it seriously, it will, inshallah, it will fulfill different ranges, most of the ranges of CEP and CEA. That's why we selected, this is one of the reasons why we have selected this IDP framework, informed design process. This is very good approach, which will really make you smart designers. there is another step, redesign the solution, where it is, I mean, you'll identify the variables that affect performance and determine which science concepts underlie these variables, which are related to P1 and P3. And what is the final thing in your IDP? The last stage, who remembers? Last one. Last one is basically communicate your achievement. And this is communication. Yeah, again, CEA is related to CEA. Yeah, all the major findings related to A1 to A5 should be documented in the final reports. Yeah, should be documented in the final report. So there are some useful resources which you can use later on. Now what I want to do is I want to show you the template what we have developed here for documenting this CEP and CEA.